Hello, my name is David Alejandro Hernandez Cuervo. I'm gonna explain the chapter 4 series impedance of transmission line. An electric transmission line has four parameters which affect its ability to fulfill its function as part of power systems: resistance, inductance, capacitance, and conductance. The four parameter conductance exists between conductors or between conductors and the ground. Conductance accounts for the leakage current at the insulators or overhead lines and through the insulation of cables. Types of conductors. In the early days of the transmission of electric power, conductors were usually copper, but aluminum conductors have completely replaced copper for overhead lines because of the much lower cost and lighter weight of an aluminum conductor compared with copper conductor of the same resistance. The fact that an aluminum conductor has a larger diameter than a copper conductor of the same resistance is also an advantage. Symbols identifying different types of aluminum conductors are as follows: AAC, all aluminum conductors; AAC, all aluminum alloy conductors; ACSR, aluminum conductor steel reinforced; ACAR, aluminum conductor alloy reinforced. In the picture we can see an example of ACSR. Resistance. The resistance of transmission line conductors is the most important cause of power loss in a transmission line. The term resistance, unless specifically qualified, means the effective resistance of a conductor is the next formula, where the power is in watts and I is the RMS current in the conductor in amperes. The effective resistance is equal to the DC resistance of the conductor only if the distribution of current through the conductor is uniform. Direct current resistance is given by the formula where ρ is resistivity of conductor, I, L is length, I is cross-sectional area. Inductance of a conductor due to internal flux. The inductance of a transmission line is calculated as flux linkage per ampere if permeability EL is constant. Sinusoidal current produces sinusoidally varying flux in phase with the current. The resulting flux linkage can then be expressed as the phasor lambda and the next formula. By Ampere's law, the magnetomotive force MMI in ampere turns around any closed path is equal to the net current in amperes enclosed by the path. The MMF equals the line integral around the closed path of the component of the magnetic field intensity tangent to the path, where H is magnetic field intensity, S is distance along path, A is current enclosed, flux linkage between 2 points external to an associated conductor. As a step in computing inductance due to flux external to a conductor, let us derive an expression for the flux linkage of an insulated conductor due only to that portion of the external flux which lies between 2 points at dA and d2. 2 points at d1 and d2 meters from the center of the conductor. Inductance of a single-phase two-wire line. One conductor is a return circuit for the other. First, consider only the flux linkage of a circuit caused by the current in a conductor 1. In the image, we can see conductors of different radio and the magnetic field due to current on conductor 1 only. Flux linkage of one conductor in a group. A more general problem than that of the two-wire line is presented by one conductor in a group of conductors where the sum of the currents in all the conductors is zero. Conductors 1, 2, 3 plus n carry the phasor currents 1, 2, and 3 to n. The distance of these conductors from the remote point P are indicated on the figure D1P, D2P, D3P, and don't have limit. In the figure we can see cross-sectional view of a group of n conductors carrying currents whose sum is zero. Point P is remote from the conductors. Inductance of three-phase lines with equilateral spacing. The equations we have derived are easily adapted, however, to the calculating of the inductance of three-phase lines. In figure we can see cross-sectional view of the equilateral spaces conduction of a three-phase line. Inductance of three-phase lines with symmetrical spacing. When the conductors of a three-phase line are not spaced equilaterally, the problem of finding the inductance becomes more difficult. Balance of the three phases can be restored by exchanging the positions of the conductors at regular intervals along the line so that each conductor applies to the original position of every other conductor over an equal distance. Such an exchange of conductor positions is called transposition. In the figure we can see the transposition cycle of these conductors. Inductance calculation for bundled conductors. At extra high voltage AHV, that is voltage above 230 kV, corona with this resultant power loss and particularly its interference with communications is expressive if the circuit has only one conductor per phase. The high voltage gradient at the conductor in the AHV range is reduced considerably by having two or more conductors per phase in close proximity compared with the spacing between phases. Such a line is said to be composed of bundled conductors. The bundle consists of two, three, or four conductors.